All right, so after today you'll be able to find displacement from a DT graph and find average velocity from a DT graph. And I see we have some quicker questions coming up, but we'll get started right away and then we'll deal with those. So, reading DT graphs, in order to illustrate the concepts of position and displacement, we're going to use a locomotive, a train moving back and forth in front of a station as it shunts rail cars. To shunt a rail car means to sort of like move it around, get it in order. Remember, the track is straight and the train station is our reference point or our frame of reference for analyzing the motion of the locomotive. Fancy words for the train station is marked 0. As we stand at the station, we know that the locomotive is 50 meters to our left. Sometime later it's in front of us, still later 40 meters to our right, and later still 10 meters to our left again. We can draw a diagram to represent the various locations of the locomotive as they are measured from a reference point at the station. Do you guys have x1, x2 on yours? You do? Okay, excellent. So x1 is at minus 50, then it goes forward to 0, then it goes forward to 40, and then it's moving backwards to minus 10. If we were to analyze the motion of the locomotive, we would need to know its change in position as it moves back and forth in front of the train station. Anytime there is a change in position of an object, we say that it has undergone displacement. That is, displacement is a change in position, right? And displacement is actually also a vector because it includes a direction. Okay, and I'll give you an example. If you go out and you do the mile run, how many people have done the mile run yet this year? Just a few of you, really? Okay. So how many laps is the mile run? Yep. 4 laps, 1,600 meters around the track. When you're all done, what's the distance that you've traveled?
1 mile.
1 mile. 1,600 meters. What's your displacement?
0.
Exactly. How come? Because you stop and start, you end up exactly where you started. You literally ran in circles. Just how many laps is it in the gym?
21.
Is that all?
Yeah. Feels like a lot from going around.
I guess, but that seems not really. Okay, so if it's 4 laps in the track and 20 laps in the gym, then the gym should be 1/5 the distance of the track. Is that right?
Yeah.
Which would be 1/5 of 400. 4 divided by 5 would be 80 meters around the gym? Yeah, maybe. Anyways. So displacement is a change in position. To determine any change in position, we would subtract where we started from where we ended up. Okay, now most people can figure this out. Like if you go back here, like the displacement from x1 to x2 is how much? How far did I go and in what direction? I went 50 meters forward. You can just look at it and figure it out, right? It's easy. But what do you do when the numbers don't work out so nice and easy like that? You need sort of a formula. You need an algorithm, a step. And it's pretty straightforward. It's just subtract, right? To determine any change in position, we would subtract where we started from where we ended up. So the formula is displacement is delta x. X stands for position. Delta x, what does the little triangle delta stand for? Change. Okay, it's the Greek letter D. And then I got here xf minus xi. I'm just going to zoom in there a bit so you can see it a little bit better. What does the xf stand for, do you think? That's right, xf. Well, the x stands for position. What does the f part stand for? Final. Final position. Xi would stand for initial position. So it's always final minus initial. Always. I only use always when it's absolutely always. Always. The symbol delta is a much used symbol in physics which indicates a change in something and always subtracts the initial reading from the final. Final minus initial. The displacement of the locomotive for the first interval can now be calculated. So we're going to go, what's the final position? From going from x1 to x2, the final is x2. Or x not x2. The final is, yes, the final is x2. Then I write xf, right? And the initial is the x1, right? xi. So this one minus this one. 0 minus 50, which is plus 50. And as Jason pointed out earlier, 50 meters to the right? I'm making it way more complicated than I need to, right? But I'm doing it using nice, easy numbers so you can see that I'm, actually correct here, that it works. This tells us that the locomotive moved 50 meters in a positive direction, which is to the right. calculate the displacements for the other two time intervals. So you're going to have to go grab a clicker, and we're going to do these here right away. So stand up for a second. So all you have to do now, I've shown you how to do the first one. All you have to do is tell me what is the displacement for interval 2, which is from x2 to x3. All you're doing is finding the displacement. And if it's negative, you have to include the negative sign, because that indicates the direction. Again, all you're doing is telling me the displacement for interval 2 from x2 to x3. Right? From x2 to x3. I don't get an answer. Going from x2 to x3. All right. I'm thinking everyone's going to get it right. The answer is 40. How do you get 40? I think it's literally, is it not 40 minus 0? Is that what it is? Yeah. Hopefully no one had to pull out a calculator to do that. Okay, right? All right. What about from x3 to x4? Let's get this one all right. You can also just look at the picture. I'll do it right here. From x3 to x4. Is it not 50 to the left? Right? So that's going to be from the final was at minus 10, and we're going to subtract 40, right? So just like adding integers, minus 10 minus 40, minus 50. I use simple numbers because you can just go to the picture and you can count, you can see. But you're going to have to be able to do it when you can't do that. So you got to learn how to do the subtraction. It's not hard. Okay. What's up with this? Oh, okay. Here are some more. Now, what do you guys have in your handout? The same thing? Okay, so we're on the second page now. Flip the page over. And it says, state the displacement for each of the following changes in position. And before you get too far, when you get to number 6, here's how number 6 works. It says, find the displacements of each interval. Which intervals have the same displacement? So you have to find all the delta x's for all of them and tell me which ones are the same. Is it A and B? Is it A and C? Is it C and D? Or is it B and C? And then they're multiple choice like that. So that's how number 6 works. So I'm going to give you a few minutes while I'm going to do my attendance for your class. And then we're going to check these. And then we're going to go into position time graphs. Okay? So they're on the back side here. Right? The first 5 are there. Number 6 is on the screen. You're going to need it. And I think I need to start it, don't I? Okay, I'm just going to leave number 6 up there while I do my pen. That's question 6. We're you have to do look at this here. It's so quiet today. I wonder who's away.
It's the hockey boy.
Oh, yeah, the hockey guys are away. Oh, so quiet today. Just a reminder here for number 6, you have to pick which ones are similar. Or the same, I guess, not similar. Have the same displacements. Let's see how we did. 100%, the answer is 6, right? Excellent. Oh, got a few different answers there. So from 2 to minus 8, so that would be minus 8 minus 2, which would be minus 10. Unless I've got the wrong answer here, do I? No, minus 10. Right? It's final minus initial, always. 8 to 0. Final minus initial. Always. 20 to minus 8. 28. 8 to minus 8. Minus 16. It's okay to make mistakes, you'll learn from them. Okay, so which one is it here? Oh, everyone got it. B, excellent. Okay, so you can see here that the displacements are the same. Even though I go from 5 to 8, so that's a displacement of 3, right? And the other one here is from minus 5 to minus 2. The displacements are the same, even though they're in different locations. Okay, that's okay. All right, so that's sort of the basics on displacement. Now let's talk about position time graphs. Now you should have done some very basic position time graphs in grade 10. At the very least, you should have just learned that straight line means constant speed, curved line means speeding up. At the very least, you should have learned that. Okay? You might not have done some actual displacement. So, knowing the position of an object tells us something about the motion of that object, but it would be helpful to know the length of time it takes to undergo that displacement. I was getting into this yesterday. Displacement and time can both be illustrated at the same time on a position time graph. The position time graph is capable of providing us with information about displacement, average velocity, and instantaneous velocity. These three calculations will be performed using the sample position time graph shown below. So here's the sample one here. It's going to appear on every screen, I think, from now on. Displacement is determined on a position time graph using the standard formula, so exactly the same way. Final minus initial. So the only thing I really need to show you is how to read the graph, right? The final and initial positions are located on the vertical axis. That's here, because it's a position time graph. And if you desire, a dotted line can be drawn from the graph to the position coordinate in order to easily identify the two positions. In other words, you can take a ruler and you can just kind of go over like this and try to figure out what point it's at if you need to. Okay? In the example graph for time interval A, now look at the top here. You see the A, B, C, D, E, and F? You see them at the top there? Okay? So A refers from 0 to 2 seconds. B refers from 2 to 3, 4, 5, 6. C is from 6 to 10. D is from 10 to 12. E is from 12 to 13. And F is from 13 to 17. And so on. Each one of the straight lines is an interval. See that, Alana? See that? Okay. So what is the displacement for interval A? Let's get rid of this highlight stuff here. Interval A is here. So what is the final position? You read it off the y-axis. What's the final position? 6. The initial position was 0. 6 minus 0 is obviously 6 meters. The number one mistake that people make is they go like this. They go 2 minus 0. They're reading the x graph, or the x-axis. That is not right. You're reading the position, the y. 6 minus 0. Guess what? You're going to do the rest. It's going to be awesome. Okay? So you are now to find the displacement for interval B, which is highlighted here for you. And then C, and then D, and then E, and then F. Okay? So I'll pause here for a moment. I'll just hit record here so that the guys watching in Thompson, the hockey boys, can enjoy this. I don't know, what are the odds that they're watching right now? Well, not right now, but no, like later on tape.
0.
0? I think they're going to. I do. Yeah? I have faith in them. I think they're going to watch it. I do. I'm just going to give them the answers here. They're probably hitting pause and making notes right now. Can't come to the rink, coach. Got to finish watching this.
Yeah, sure.
Okay, maybe I'm exaggerating that. Okay, now you have to determine the average velocity for each interval. How do you find average velocity? The formula is displacement over time. So interval A, are you guys on the right page? No? In all cases, you're going to take the displacement and divide by the time. The interval A displacement was 6 because we figured that out already. Right? How long is interval A? It's from 0 to 2 seconds. So 6 divided by 2 is 3 meters per second. Okay, so now, chance for you to redeem yourself. Determine the average velocity for intervals B, C, D, E, and F. You have to take your displacement. If you got it wrong, take the right answer. Take your displacement, divide by the time. Go.
That's all you do.
That's all you do. Displacement, divide by time. For A, so that's for B, C, D, E, and F. Well, number 5 is one special question, right? Okay. Can you answer number 1?
Where are you looking? Because I'm like really confused.
Yeah?
I didn't even do the right questions last time, so. Are we looking at the graph or are we looking at these? Like, I'm confused. And then we put the displacement on.
Now we're here.
Yeah.
Okay? To determine the average velocity, the interval B is up here. Okay? And this is the question, the interval B is that's B, that's C, that's B, that's C. Do this exactly. Okay? For some reason we're having trouble. Are you able to enter? Jason, can you enter answers?
Yeah.
Yeah? For number 1?
Oh, okay, for all of them.
Okay, well, I mean for any of them, right? Because it says start this assessment, so.
Yeah, I can.
You can too?
Yeah.
Yeah.
Oh, I'm on this one here, it looks like. Okay, now you can start with question number 1. You might have got kicked out.
Oh.
Yeah, I clicked the wrong one, I think.
We're just doing one at a time then?
Yeah. Is it one at a time?
Yeah.
Oh, okay. I gotta fix that. Okay, so let's do number 1 then. Okay, so you're only finding the average velocity for interval B. That's the only one you're doing right now. Okay? Remember, it's displacement over time. What was the initial displacement? What was the correct answer for the displacement for B?
0.
I think it was 0, right? So this is going to be 0 divided by? 1, 2, 3, 4. From 6 to 2. 0 over 4. Please, everyone, get it right. 0 divided by 4. No, you gotta use it. Oh, yeah, no, you can get it second. Raphael, you gotta enter here. 0 divided by 4. Please, everyone.
Hey. Checkbook right there. Checkbook.
0 divided by 4. 0. Remember I told you it when a flat line means it's
0.
stop. What does stop mean? Not moving. What's your velocity of your stop? 0. 0. Okay. Let's try C. From 6 to 10, you're going to take the displacement and divide by the time again. What was the correct answer for the displacement before? Do you remember? Interval C, was it?
Negative 16.
Negative 16, I think you're right. Minus 16. Down. Minus 16. How much time is it from 6 to 10 seconds? Minus 16 over 4 is? Minus 4, you guys. You can do this. Interval D from 10 to 12 seconds. Okay, come on, you guys. Let's get it. Come on. We can do it. Everyone's got to get this one right.
Oh, I typed the wrong number. Oh, no.
You can go back, I think.
No, I can't. I already know that. Everybody, 7.
It says number 2, yeah. That's the only one that's running, I think.
Oh, we're on to number 3?
Yeah. We're doing interval D, right? The one that's on the screen. How fast is it going in interval D? Come on.
7.
What does a flat line mean?
0.
Stopped! Flat line means stopped, or 0 meters per second. Flat, stopped. Okay, come on. Come on, you guys. We got 2 left. Now, well, here, I'll wait a second.
It's not letting us look at it.
Oh, because I haven't turned it on yet. Find the slope for interval F. All right, here we go. We'll see. The slope is 1. How do I find the slope? Okay, watch. If you're still not getting this, please watch. I'm trying to figure it out. Oopsie, that's not what I wanted. Okay, you're trying to find the slope. Slope is like y2 minus y1 all over x2 minus x1, right? And those refer to the x and y variables. So the slope here, the displacement, v equals d over t, it goes from, final position is 0. 0 minus, what's this position? Negative 4. 0 minus a minus 4, which is plus 4. And if you have to, you can just go 1, 2, 3, 4. Count up 4. It goes up 4. Rises 4. Right? Rise over run. How much does it go over? 1, 2, 3, 4. Or if you want, you can say, well, that is... What's the x position here? The time. It is 15, 16, 17. Here it is 13. 17 minus 13 is 4. 4 divided by 4? 1 meter per second. The slope is the velocity. Write that in there. I hope you would have learned how to do slope before. The slope is the velocity. This is true on a PT graph, position time graph. Okay? You have to find the slope. Okay, last question. This is the one everyone's going to get right. Given this position time graph, determine if this represents a real-life situation. Could you ever have a position time graph that looks like this? Yes or no? Does this represent a real situation? Yes or no, it does not represent a real situation. You put Y or N is on your buttons. Does this represent a real life situation? Yes, it does, or no, it does not. You got 50-50, I guess, if you're guessing.
I mean, you shouldn't be guessing.
You shouldn't be guessing. You should know this.
Actually,
Maybe he'll be a genius. All right, here we go.
oh my God, wait. You can't go back in time.
The answer is no. This is not a real life situation. I hear a lot of people saying you can't go back in time. That is true. I prefer to acknowledge it as at the same point in time you can't be in, don't pack up, you can't be in 2 different places at the same time. Right? Have you done the vertical line test at math yet? What does the vertical line test say, Anna?
Yeah, or quadratic. I'm Manitoba and in Canada. If you have a quadratic, you can't. Versus line test.
If a line touches, then it's not a function. Okay, so in all cases, don't pack up, you guys. I'm almost done. Don't pack up. In all cases, position is a function of time, because if you draw a vertical line, you can only be in one place at any point in time. So right there, right? What does this make it? It makes it not a function. Okay? So you can't go back in time. Exactly. Okay. Normally, I have enough time to give kids time to work on this. Okay. I'm going to assign a little Thanksgiving homework. Okay. There are only two graphs. There's only two. I'll be nice. You guys do the first one. You gotta have the first one done. If you find out that it only takes you like 3 minutes and you can do the second one, then go ahead and do it. But you only have to have the first one done. I am going to check, Jason, because I have a big meeting.
I did.
I'm gonna stay right.